Well, hello and welcome again to our journey into linear algebra. And in this section we're going to be looking at the exponential of a matrix. So the basic question is, can we make sense of raising, okay there, can we make sense of raising the number e to a matrix? Since after all we know from the theory of differential equations, lots of typos today, the theory of differential equations, that e to the x is a very useful function. In particular, so presumably e to the a, or e to the at, may well also be very useful and very interesting. So in particular we're going to try and make sense of the matrix e to the at, where t is a real variable. This is analogous to e to the kt, where k is a real number, and now we've got a matrix up here. So the key to doing this is to use the Maclaurin series for e to the x and see what happens if we replace x with a, or at. So firstly, to try and make sense of e to the a firstly, so here's our Maclaurin series of e to the x. It's that beautiful series, 1 plus x squared on 2 factorial plus x cubed on 3 factorial and so on, which we can write in sigma notation. This is an amazingly simple series for such an interesting function. So we're going to make the following definition. We're going to replace the x here with an a, and replace the 1 with an identity matrix to make sense of it all. And we're going to define x of a, or if you will, e to the a, as simply 1 on k factorial times a to the k, and we take a sum. In other words, that's identity plus a squared times 1 on 2 factorial plus a cubed times 1 on 3 factorial, and so on. Now there are questions of convergence here, and I'm not going to worry too much about this, simply to say, roughly speaking, if A is an n by n matrix and m is the maximum absolute value of any entry of A, then every entry of a to the k has absolute value at most n times capital M to the k. I'll leave you to think about why that's true. So every entry is a power series which converges by comparison with this thing. So if we look at each individual term in this this sum of matrices, then the largest combination of terms we're going to get is this, and this converges to e to the nm. And so this, in fact, this definition up here is going to make sense. It will converge for any matrix A that we like, and that's because the exponential series converges for all x. You can use other power series, by the way, to define matrix functions such as the cos of a matrix or the sine of a matrix and so on. Log, of course, is a little bit more complicated, but here we're just going to confine ourselves to the exponential function. Now we'll begin by looking at a very special case when A is a diagonal matrix, and we'll see that that turns out to be very easy to do. And as an example, I'm going to consider this diagonal matrix 5, 0, 0, minus 7, and we're going to find e to the dt. So here's the worked example to this. Here's our matrix D, which is 5, 0, 0, minus 7. And by definition, e to the dt is I plus dt plus d squared t squared on 2 factorial plus d cubed times t cubed on 3 factorial plus, and so on. Now, when we've got a diagonal matrix, then of course the nth power of that matrix is easy. It's just 5 to the n and minus 7 to the n. Put some brackets in there. Minus 7 to the n. And so when I plug that into here, when I write this out, I'm going to get 1. In the first position, I'm going to get 1. I'm replacing I've got dt here, so I'm going to get 5t. Then I'll get 5t all squared on 2 factorial, 5t all cubed on 3 factorial, and so on. The second entry is going to be 0, because I'll get 0 in here, and so when I look at this entry here across here, I'm going to get 0, same down here, And this one I'm going to get 1 minus 7t plus 7t squared and 2 factorial minus 7t cubed and 3 factorial and so on. Now of course this is just e to the 5t, and this is just e to the minus 7t. And we feel a general result coming on here. If you've got a diagonal matrix, so in general I can write down that if you've got a diagonal matrix with, say, lambda 1 to lambda n down the main diagonal and zeros everywhere else, then e to the dt is just e to the lambda 1t all the way down. So you just take the exponential of the main diagonal here with a t in it and zeros everywhere else. So we can easily exponentiate a diagonal matrix, and that's very nice that we can do that, and we'll see that we can then extend that to do any matrix at all. So from the above example we surmise that in the case where our matrix is diagonalizable, we have the following, that we can now as long as the matrix is square and diagonalizable, then we can work out e to the at. So if the matrix is square and diagonalizable, that means there is a p matrix, a change of basis to an eigenbasis, where we can write A as p d p inverse, where d is diagonal. And we're going to show that then e to the at is just p times e to the dt, that's exponentiating this diagonal matrix here, times p inverse. And the proof of this again is fairly straightforward. That's worth going through. It's a fairly straightforward proof. So here's the proof. We've got p is equal to p d p inverse, and as you've seen before many times, if you write this, you take a to the n and you write this down n times, the p inverses and the p's all cancel in the middle, except for the one at the beginning and the one at the end, and we just get d times itself n times. So going back to our definition of e to the at, well, it's just, there it is, there's a definition of e to the at. And now I'm going to replace the a, or the powers of a, using this formula here. So I'm going to get p times, I'm going to write, well, I'm going to leave the identity as the identity, and then a is going to be p, or at I should say, is p dt p inverse, and then I plug it into the second one, and so on along. Now out of this I can factorize a p out of this end, and then a p inverse out of the other end. So if you look at the first term, we get pi p inverse, but that's just I. Then I'll get p dt p inverse, and that's the term there, and so on through. So I can factor a p out from the left and a p inverse from the right, and this expression in here, of course, is just e to the dt. So there's a nice little proof of the fact that we can, if we've got a diagonalizable matrix, then we can find e to the at fairly easily. So in the case where our matrix is diagonalizable, then we just proceed as follows, and I'll just do it by example. So I've got the matrix 3, 4, 5, minus 5, and we want to find the exponential of this matrix. As we'll see, the answer, the e to the at, it's amazing we can do it in the first place, but the answer is relatively complicated, as we'll see, even in the diagonal case. So firstly, we need to find the eigenvalues and eigenvectors so we can get our P matrix. So I've done this longhand, so I set the determinant of A minus lambda I to be 0 to get me the eigenvalues. So that's lambda minus 4, sorry, that's, well, it's 3 minus lambda times minus 5 minus lambda, which I can rewrite as lambda minus 3, lambda plus 5 minus 20. Expand it out and factorize. And there are the eigenvalues, 5 and minus 7. So as usual, we get the eigenspaces, so I'll subtract 5 off the main diagonal. I get minus 2, 4 up the top, so I'll need 2 and 1 for the eigenvector. And for the eigenspace for 7, we subtract 7, we add 7 to the main diagonal, and we find we get 2 minus 5 for the eigenvector. You can check that there. And now we put our, so we have P inverse AP as D. We put our P matrix to be the matrix of eigenvectors, and the diagonal matrix consists of the eigenvalues. So, using our little theorem we just had, e to the at then is p e to the dt, P inverse. So there's my P matrix, there's e to the dt as we found before, and then the inverse is here, divided by the determinant here. And I've just multiplied the whole mess out separately, and we get this matrix here, which is looking pretty complicated now, got lots of different terms in it. But that's what happens when you work out the exponential. It is, in some sense, amazing we can make sense of an exponential of a matrix, or a matrix exponential, I should say, perhaps. But the answer is, as you see, moderately complicated, even for a 2 by 2 matrix. Now, one likes to be able always in maths to check that the answer makes sense, and one way of doing that is to put t is equal to 0. Because as you might expect, put t as 0, you're going to get the 0 matrix here, and you would hope that the e to the 0 matrix is the identity, and in fact if you go back to the definition it's obvious it must be. And you can check your answer here. If I put t to be 0, I get 10 plus 2 is 12, divided by 12 is 1. 4 minus 4 is 0, 5 minus 5 0, 2 plus 10 is 12, divided by 12 is 1. So as a nice little check, when t is 0, we obtain the identity matrix. Well, look at one more example. Again, you might like to stop the video at this stage and try doing this one yourself, and then compare what answer you get. So we're going to find e to the at for this matrix, 3, 6, 1, 4. So I said you might like to try that separately and see that you get the same answer. Here, however, is the worked solution to this. So here's our matrix, 3, 6, 1, 4. I'll leave you to check. The eigenvalues turn out to be 1 and 6. And if you subtract 1 off the main diagonal, then the eigenspace for 1 off the main diagonal will give you 2, 6 here. And so I need 3 of those and minus a 6 to give me dot product to 0. The eigenspace for 6 is 2, 1. Similarly, we do P inverse AP to be D, so our P matrix is just the matrix with the eigenvectors in it, and there's the D matrix consisting of the eigenvalues. Now again, e to the at is just p times e to the dt times p inverse. So there's p. Now e to the dt is easy. To exponentiate this, you just exponentiate e to the, so it's e to the 1t times, and then e to the 6t here. And there's the inverse, and I put the determinant out the end here. And again, I've just expanded all this out longhand, and I get this as the exponential, which I hope if you did this yourself, this is what you would have gotten. And again, you can double check the answer makes sense. If you put t to be 0, you get 3 plus 2 is 5 over 5 is 1, 2 plus 3 is 5 over 5 is 1, minus 1 plus 1, minus 1 plus 1 is 0. And so that gives us a nice little check that the answer makes sense at the end. If you put t as 0, you better get the identity matrix. Now that works beautifully, and it works not just for 2 by 2 matrices, but in fact for general n by n matrices, provided the matrix is diagonalisable. Now of course the arithmetic can get much more complicated. Once we get to 3 by 3s, we're going to have to invert a 3 by 3 matrix in general in order to get the exponential, but at least one can do it. In the case of a diagonal matrix, it is possible to do. In the next section, we're going to have a look at what happens when we try and deal with a non-diagonalisable matrix, and that's where the Jordan form is going to come back into its own, and we'll have a look at what happens when you try and exponentiate a Jordan form.